considered no, naturally occurring, or no, we can also no, create them in the laboratory. No? We have mentioned also the different types of magnets, no? Those that are slightly, no? So they are slightly affected by magnetism. But if you have an actual observation of this, no, like an aluminum, if you put a magnet on aluminum, you will rarely see it move. No, so there's very little effect on aluminum. Now, diamagnetism are described as materials that are repelled. No, so if you put a magnet there, they kind of move away. You know? So if you will try to suspend, for example, mercury. No? So mercury is a liquid material. If you put a magnet on mercury, no, then you'll notice that mercury will move, no, away from the magnet. No? So maybe that's one way that you can also no isolate mercury. So they are kind of repelled no by magnetism. And then we have ferromagnetic materials that are now no very much affected by magnetism. No? Now their main component there is of course iron. Steel no is an alloy. It is a mixture of some iron and some other metals. No? And these are the ones no that contains no permeability that is in hundreds or several thousands, no? Which of course no allows magnetism to get in through into the material. No? Now we describe this concept of permeability and retentivity no, as characteristics no that allows probably no the residual stay of magnetism and how much magnetism can be absorbed into the material. No? So retentivity, there are materials that can hold magnetism for a long time, but there are those that are exposed no, and can absorb magnetism but cannot hold it long. No? So that is dictated on by a value called permeability. Here are some things that we see with the effects of magnetism. No? And looking at this diagram, no, if we hold a piece of compass, no, that compass when placed beside a bar magnet, the needle of the compass will now behave, no, or will now move in several directions, no, depending where you place it, no, relative to the bar magnet. No? So the direction of the arrow or the pointer of the compass no is changing as you move from the north pole of the magnet to the south pole. So again, no, we can actually not trace these lines around it, no, which are invisible by probably using no, the compass. No? Now, aside from that, now we can visualize also these lines of forces. If we put no, some iron filings on our magnet, no? But of course, to put iron filings, you have to separate it from a magnet by putting a piece of paper. So if you put a bar magnet and then cover it with a bond paper, and on top of that bond paper, underneath underneath it is the magnet, no? Then you can pour the iron filings on top of the paper, and you will now trace, no, or be able to see, no, these invisible magnetic lines, no? And we can now see that, no, through the actions and the behavior of the iron filings. No? So iron filings is very much affected by these imaginary lines. No? Now, what we see here is that the lines of force starts from the north and somehow ends in the south. But in reality, no, if we will look deeper into the material, these lines of force actually passes inside the magnet, no, in one continuous loop. No? So I call it as a loop. No? So this line here, these magnetic lines, no, around the magnet is actually no passing even inside it. No? Again, no? And then that line is never cut. No? It is always appearing to be rotating in a manner. No? If I'm going to describe the rotation here, no, of the magnetic lines below to be somewhat like counterclockwise, the one below, no? But the one above, we can describe it as clockwise in direction, no? But it is going around the magnet, no? Now, here are some misconceptions about magnets, no? So we thought of the magnetic poles to be somewhat only, no, on the surface, but in reality, no, it is even inside the atomic particles, no? So another question, splitting the magnet, no? And of course, we were able to answer this, no? And we answered that by using this domain theory, no? Now, the domain theory is telling us, no, that the nature of the magnetic north and south poles of the magnet goes even to the microscopic level, no? And if you have a piece of iron or steel, no? And that is illustrated by this first diagram above, no? If that is a steel and the orientations of the magnetic domain, no, or the domains, no, are randomly, no, positioned in this manner, you can never make this steel, no, into a magnetic device, no? Now the only way that you can make it magnetic is when you let the magnetic domains change their direction and somehow realign them, no, to make them what they look like in the second figure below, no? Now, in the second figure below, you'll notice that somehow, no, there's some sort of a direction where all these magnetic domains are now behaving, no? They are not randomly, no, spread out, no, like the one that we see above, no? Now, when we have this, no, then of course, no, we will have now a kind of a north and a south pole to this, uh, if to this metal, no? So again, no, changing one state and making it now magnetic, no, in the diagram below. So again, we can explain that by virtue of the magnetic domains, no, or the domain theory, no? Now the arrow usually, no, indicates the north pole, and maybe the tail there is your south pole, no? So if you make them, no, all move in somewhat, no, a direction from left to right, then we can make the material magnetic now, no? Now ways of magnetizing, no? So we mentioned this also. So we can either heat up a material to make it magnetic, no? So now one way that they do that, first of all, no, is to put powerful magnets, no, in between an unmagnetized material, no? So if I'm going to have here a bar magnet, no, two of them, I'll have two bar magnets here. And what I will do with these bar magnets, I'm going to insert in between them, no, a smaller metal, maybe, no, a rod or another piece of metal, no? So this metal in between is not magnetized, no? Now our magnets, no, we are going to position them, no, with two of their poles, no, exactly, no, facing each other, no, and somehow squeezing the metal that is in between them, no? So we have two opposite poles and we subject the metal in between, no, to these two opposite poles, no? Now the domains earlier that we've seen, no, maybe in this figure, it is not yet, no, arranged, or they are aligned, no, not they are not aligned properly. So by doing this, no, this will give the opportunity for those domains to realign themselves, no? Now we can either stroke this, no, with another bar magnet, no, meaning stroking, no, you put on the side of the unmagnetized metal, no, another magnet, and you rub, no? So somehow stroking or rubbing is the same process. You rub it in one direction, no? From left to right process, no? And then little by little, this magnet that is in between these two other magnets will now become magnetized. Now the magnetic domains will now realign themselves. Now another way to do that, not to give those magnetic domains opportunity to move, is to heat up, no? You can apply heat to the metal in between, or you can hammer it, no? Hammering also, no, provides a shock to the atoms, and the atoms and or the microscopic particles inside will have the opportunity now to move, no? So by providing some kind of an energy or a shock. So again, no, methods or ways of realigning the domains. No? So once the domain is uh, are aligned, no, then you will now achieve, no, a magnetic material. Now another method is by using a coil. No? So I hope I can draw a coil here. So a coil usually is drawn like this. No? So I am not drawing it properly, siguro, but you can think of a coil as something like a spring. No? But you should make it a little wider, no, the holes of the coil, so that you can insert this metal in between the coil. No? So a coil is what? A winding of wires, no? And then you simply stretch it, no? Spread it. And then now, once you provide a battery in between this wire, no? You can now put a battery there, and therefore, current will now flow in the wire. No? Now, once there is current flowing in the wire, if you leave a metal, no? If this is a metal initially that we inserted in between the coil, you'll notice that that metal, no, after some time, no, of letting current pass through the wire, if initially this metal that you place inside is not magnetized, now after a while, no, maybe an hour or more, no, when you remove the electricity, no, when you unplug this and remove the metal, you'll notice that the metal now will become magnetized. No? I think they call this process as the Alnico process. No? But in here, now we simply put, no, a direct current, no, into a coil of wire. No? So again, no, this is also considered as one of the techniques in magnetizing material. No? Okay, now if you want to demagnetize, then of course you can reverse that same process as well. No? Okay, so anyway, those are some techniques that we can apply, no, in magnetizing our material. Okay, now allow me to erase this. No? Okay, so here is what we call magnetic induction. No? A permanent magnet can induce temporary magnetism in a soft magnetic material. No? This causes attraction but cannot cause repulsion. No? So on one end, no, so this is our paper clip. No, you'll notice that the paper clip is not magnetic. No, but once you place it on a magnet, this paper clip is turned, no, into a magnetic material because it also attracts other paper clips. No, so what we did was we induced or we forced magnetism into this paper clip. No? So that's the term magnetic induction. No? Making one material magnetized, no, by virtue of another, no, magnetic material. No? So here now we see some forms of attraction. No? So we term that as magnetic induction. Now, if we have a coil of wire as well, we can also, no, achieve or have, no, this this effect, guys, which we call as the right hand rule. No? Okay, now if we will try to remove the wire here, no? So if we have a rod, guys, no? If we have a rod, merely a rod there, no? And then we will try to remove this wire at the top. No? So do not add the wire there first. Now, uh, for this rod that we've erected, no, or we made vertical, butangan natin just sang papel, no. We are going to let a paper pass through the rod, and then initially, so you have a rod only in a paper. Now you'll notice that if you'll pour iron filings on the paper, nothing happens to the behavior of the iron filings. No? The iron filings now, without these wires and current, the iron filings will just simply be spread out, no, in this paper. Now, however, after a while, no, if you will now repeat the process, but this time you add these wirings at the top, no, to allow a battery to be attached to this wire, no. Maybe the positive end of the battery here, and then the negative end of the battery at the top, no. Now, once the battery is added, then we know that there's going to be current flowing, no, into this wire, no, that we attach to this rod. Now, this time, after attaching the battery and this wire, no, and making current flow, if you're going to repeat the process of pouring again, no, if you pour again some iron filings, now the iron filings will not simply be spread on the paper, but the iron filings now will be seen as something like going in circles. No? So what made the previous illustration, no, different to the next one when we added this wire? No? Of course, the 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 thing that happens to the iron filings that they now behave, no, as if there's a force that forces them to form circles. No? Kung wala ni ang wire kagang current, nagalalapta lang da sila ang iron filings. But kung butangan mo na sang wire na may current, nagapalibot ang iron filings. No? The iron filings will tend to be pushed, no, in this specific manner na nagalibot-libot sila. No? Now, what could have caused the movement of the iron filings? We can only attribute that, no, to a presence of a force, and that force is definitely magnetic. No? Because iron is only, no, is influenced a lot by magnetism. But where did the magnetism come from when you simply have a wire with a current and there's no literal magnet here? No? Okay, so that question is answered now by this principle we call as right-hand rule. No? Now, according ko na sa right-hand rule, gali, once there is a current that passes through a metal, a magnetic field is set up. No? Even though wala magnet din. No? May ara ko nga magnetic field nga ma-set up once may current, kagangina a current will pass through a metal or a rod, no, like this. Kaga may direction gina ngaton nga paglibot sa ngaton di nga magnetic field, no? Because, no, according sa right hand rule, if you are going to grab, no, looking at the hand of this person, if you are going to grab this metal or rod, ang imo nga thumb, guys, no, kung ipa-point mo ang thumb to the direction of the current, no, pagka nabalaan ang current, pasaka siya from this direction and then it goes up the rod. Paano na ito nabalaan? Because we know current always travel from the positive end of the battery to the negative end. No? So we call that as the conventional current flow. Now, as current passes from positive to negative, then it would seem na sa diri nga rod, this is going up ang current. Dira, no? That's why if you use your right hand, if you grab the rod, no, then ang imo thumb will point up the same sa direction sang current. Now, ano ni karon ng obra sang iban mga finger, ang apat, amo na ang imo karon nga direction sang magnetic field. No? Ang imo nga finger, ang imo nga kuko, ni bala ko ng tawon mo, nagalibot siya, no, in a manner nga halindi pakadto daw. No? Okay? So, again, no, if you try to grab it, no, ang imo finger or ang imo nga mga kuko will point the direction of the magnetic field. No? So, man nga ang nature sa magnetic field, there is circular. No? Kaya nagalibot siya sa metal. No? And hindi lang na siya isa ka magnetic field. No? Damo na sila. No? And subong ang niwang-niwang ni nga wire or metal rod, actually nagadako siya by virtue of the magnetic field that is, no, happening all throughout the length of the metal. No? Ang bilog yan nga length, may magnetic field na gali sa gwa niya. No? And as a matter of fact, tanan nga wire nga naga-carry sang current amo nang ila batasan. Do you follow? So what if ko na nga ito nga gina-deal subong is a coil of wire. No? Parehas ni kaina sa nga ito illustration. This is very similar to the illustration that we have, no, nga we deal with, no, a metal that we are going to magnetize. No? So this is our coil of wire. We call this coil that we stretch. No? Since gin spread out naton ang coil naton, we call it as a solenoid. No? The word is a solenoid. But if you are going to make simply a coil nga flat lang, no? Magdara mo lang sa ginlibot-libot, then that's a coil merely, no? But once you stretch it and it appears like a spring, now we call that as a solenoid, no? Now, what can we do with this coil of wire? One thing that we can do, we can let a battery, no, be attached to the wire, no? And once you attach the wire into, once you attach the battery into the wire, then there's a possibility that current now will go into the wiring, no? So kung diin ang positive side ng battery, dito na masulod ang current, no? And again, no, that's how the current goes, no? So we are going to illustrate this in the next video. Okay, we have less than a minute na lang, no?